Okay, so now we are putting the two things that we heard about together, measurement-based quantum computation and contextuality, in a specific example. And so this is the work of Anders and Brown that I'm now discussing. So what we are talking about now is a 3-qubit example. So we want to convert this Merman star, this contradiction, into something that works for us, into a quantum computation. It's a 3-qubit quantum computation on a 3-qubit GHZ state, so don't expect too much. We will not solve all of mankind's problems with a 3-qubit quantum computer. In fact, what we are doing is we will evaluate an OR gate. That's all we do. We execute an OR gate, and as we go along, I will tell you why this is significant from a fundamental point of view. Okay, so but let's begin with our setting. So we have our Greenberg one-siding state with 3 qubits. So let's label them. And each of these qubits is now measured in one of 2 bases, namely the X basis or the Y basis. So remember what I told you earlier, so there is 2 bases generally to measure each qubit in, and this time these bases will be X or Y. So X we will denote as Q equals 0, and Y we will denote as Q equals 1. And this applies to all of the 3 qubits. Okay, so this is our setting. And to complete it, let me get back to those classical site processing relations. So this is what I explained to you in our first part, basic facts about measurement-based quantum computation. Every measurement outcome is random, and so what you're interested in is the correlations among these measurement outcomes. And so that leads to classical site processing relations. And the first is this earlier relation adapted to this concrete scenario. So we have 1 bit of output, and this is going to be the sum of the 3 measurement outcomes. Okay, so this is the first relation, relating the output of the computation to the measurement result. Okay, and then we have these other mod 2 linear relations that relate the input to the computation to the choice of measurement basis. Okay, so remember what this does is it computes an OR gate. We compute an OR gate. Okay, maybe I should tell you what is relevant about an OR gate. I mean, probably today every dishwasher in the world does 100 million OR gates per second. So why is the OR gate important? The OR gate is a non-linear Boolean function. And so suppose we wanted to operate our measurement-based computing device without a quantum resource. You would just use the classical site processing that we have available. We just make it more efficient and just dispense with the quantum resource altogether. If we do that, then all we can ever do is the classical site processing that is provided, and that is mod 2 linear relations. And so with the quantum resource, we can do more. We can do nonlinear Boolean functions and in addition, and that boosts us from a very limited computational model, at least to classical universality. It's not quantum universal, but it is classically universal. So with this quantum resource, in this setting, we tremendously boost the computational power. And that's why this OR gate is important. So the OR gate has 2 bits of input. So this means that M equals 2 bits of input. This is the number of input bits, if you remember. And let's call these bits A and B. So in our earlier notion, first input bit, let's call it A, and second input bit, let's call it B. So that's what we are talking about. So now, let me specify those linear side processing relations. So for qubit number 1, the choice of measurement basis is given by this relation. Yeah? So what Q1 is decided by whatever the first bit of input is. Q2 is the other bit of input, and for the third qubit, Q3, is the sum of the two mod 2. Okay, yeah? You easily verify these are all mod 2 linear relations. Okay, so this is how the classical side processing works out in this specific case. Okay, so now let's verify that an OR is computed. So let's make a table. Let's go through this case by case, at least for the first few cases. So let's talk about the input first, and then about our choices of measurement bases that are applied, and then finally about the output that we are interested in. So let's make this table, and I do as many cases as I can fit on the board, which is probably 2. Case number 1, A is 0 and B is 0. So now we can go through these formulas and figure out what the measurement bases are. Well, if A and B are 0, this means all the Q values deciding the measurement bases are also 0. And so what this means is that we are measuring the qubits 1, 2, and 3 all in the X basis. So this is this measurement context over here. And now you remember, both classically and quantum mechanically, it holds that upon measurement, when I measure these 3 local observables, then the corresponding eigenvalues, they multiply to the eigenvalue corresponding to that observable over here, which is +1 because we are dealing with a Greenberger-Horn-Zeilinger state. Yeah? So this means eigenvalue here times eigenvalue here times eigenvalue there equals +1. Yeah? And maybe one more thing to add, eigenvalues lambda, or measurement outcomes lambda, are related to our outcomes written in this way, in this fashion. Okay? So if the eigenvalue is +1, this means outcome is 0. If the eigenvalue is -1, this means outcome is 1. So this is how we write it. Okay, and if the product of these eigenvalues needs to be +1, what it implies for these mod 2 values is that their sum modulo 2 needs to be 0. Yeah? +1 identifies with 0. Okay, so this sum mod 2 is going to be 0, which is precisely our output. And so in this case, we are getting output value of 0. Okay. Yeah. Okay, so this was the first case. I have space for one more, and that's not really a constraint because the 3 subsequent cases are all the same. So you can complete the table for yourself. Okay, so A equals 0, B equals 1. We just go through our classical side processing relations. We find that Q1 is 0, Q2 is 1, Q3 is also 1. Okay, so this means qubit 1 is measured in the eigenbasis of X, X1, and the other 2 qubits are measured in the eigenbasis of Y, So this is qubit 2, this is qubit 3. So this is the context that we are now dealing with. Okay, in our same game as before, the measured eigenvalues here times there, they multiply to the eigenvalue of this, which, because we're dealing with the Greenberger-von-Seilinger state, is -1. So the eigenvalues multiplied to -1 means the corresponding values S add up to 1 modulo 2. So the output in this case is 1. Okay, so this was the second case. Now you go through the other two cases that remain, and you fill in. You'll be hitting these values here, this one and that one. So the output will be 1 in these other two cases as well. And so this means, if you check this logical table, that an OR gate is computed. So let me write it down, because it didn't quite fit here. So we have the input, output, 0, 0 gives you output 0, 0, 1 gives you output 1, so that's the two cases we did. Then, well, the other two cases is like the last one we did. So 1, 0 gives you output 1, and 1, 1 also gives you output 1. And this is the OR. Okay, so we verified indeed we do an OR gate, and again the significance of this result is that the OR gate is a nonlinear Boolean function. So we are getting more computational value out than we have been putting in by the ability to do the classical side processing. So there is a gain, even though admittedly it's a very, very simple computation. Okay, so that's the bottom line from this example. Contextuality is related to the nonlinearity of the Boolean function computed. And we will see in the last part of this lecture that this is not just the case in this specific example, but in generality. But again, maybe let's stick with this result for a second. Merton's law was the device through which the connection between contextuality and measurement-based quantum computation was made, and that's in a paper, if you want to read it, by Janet Anders and Dan Brown from 2009. It's a PRF.